So we have question 10, which is asking about the charge, different attributes in a with or without the dielectric in a parallel plate capacitor. And the radius is 1.7 centimeters. The distance between the capacitors is 0.0005 meters. The constant is 2.5, and it's a 9-volt battery in series. And with a parallel plate capacitor, which is on the positive and negative side. And with the dielectric inside, it will create its own electrical field that's opposite of the direction. And we're supposed to find charge, potential, electric field with and without dielectric.
So first off, we'll go ahead and find things without. So this is going to be without the dielectric. And we'll start off by finding Q. So first off, we need to find what capacitance is, which that is equal to epsilon naught area over distance, which is equal to 8.85 times 10 to the negative 12 times the area is just 35 times r, is 1.7 centimeters squared over the distance is 0.0005 meters. This gives us a capacitance of 1.607 times 10 to the negative 11 farads. Now we use this capacitance to find our Q, which is equal to capacitance times voltage. So we use that capacitance and we times that by our 9-volt battery, and we get 0.14463 times 10 to the negative 9 coulombs, or 0.14463 nanocoulombs. And that's our charge. So then our voltage, or our potential, is just going to be equal to 9 volts. So, and this is because, so without this, that is just gonna, it has to be equal to our, what the battery is sending into it. And then finally for E, E is going to be equal to, if you look on your equation sheet, E of capacitance is equal to this equation here, and we know that that is equal to Q divided by area, and that's all over epsilon naught. And this is going to be equal to this charge here, 463 times 10 to the negative 9, all over 5 times 1.7 over 100 squared for our area, and that's all going to be divided by 8.85 times 10 to the negative 12. When we do that, we get an electric field of 18,000 volts per meter. And so that's going to be everything without. And now we'll come down here and we'll do things with. So now we're going to do everything with the dielectric. So find Q. It's kind of the same process. We have to find our capacitance first. So find our new capacitance. These equations came out of the video, so if you haven't watched the videos for day 4, go and watch those, and they'll kind of explain this. C, the new one, is going to be equal to our K value times our capacitance original, which is just going to be 1.607 times 10 to the negative 11, and then our K value is 2.5. And that gives us capacitance of 4.0175 times 10 to the negative 12 farads. We can use that to find our Q, which is going to be equal to CV. But before we find our charge, I'm going to go ahead and find our voltage since we need that for this. So our voltage is going to be equal to, this equation comes out of the video as well, 1 over K, the original, is equal to 1 over 2.5 times 9 volts, which gives us a voltage of 3.1 volts. So that's our new one. We can plug that in up here. So take our capacitance of 4.0175 times 10 to the negative 12 times with our voltage, 3.1 volts, and that's going to give us a new charge of 0.01245 nanocoulombs. Now finally, we can find our electric field, which is going to be equal to our electric field original over K, and this is going to be equal to 18,000 over 2.5, which gives us 7,200 volts per meter. And now if we remember what Laura said at the beginning, so we have, here's our two sides of the capacitor. We have our electric field without this dielectric, but when we add this, it gives us a little electric field, which we just barely calculated. So we have to actually add these together, or minus this smaller one from the bigger one, so we can figure out what our total electric field is. So if we go back over here to what we just calculated, we'll go ahead and take our original minus the one that we just calculated, get our total. So we'll have 18,000 minus 7,200. Sorry, 18,000 minus 7,200, and that will give us 10,800 volts per meter. And that's our total electric field.